Hello, I'm Negin from Sharif University of Technology, and I'm going to present one of our greatest work at HBK Laboratory called NURA, a framework for supporting non-uniform resource accesses in GPUs. GPUs are widely used in various processing domains, from image processing to deep learning and scientific simulations. Despite the ongoing global chip shortage, the GPU market sees significant growth in 2021. According to the figure from NVIDIA, its worldwide revenue is increased by 4 times in 2021 compared to 2015. Modern GPUs typically have many processing cores grouped to form SMs in NVIDIA terminology. This figure shows an architectural view of contemporary GPUs where all SMs use a shared L2 cache. Each L2 cache bank is connected to a memory controller. Each SM has dedicated compute or memory resources for supporting a wide range of applications. Each GPU kernel consists of a large number of threads. The threads are grouped in warps and warps are grouped in CTAs. In a warp, all of the threads run in lockstep and all of the warps in a CTA are allocated to a single SM. GPU kernels are composed of several CTAs that are distributed across the SMs based on the available on-chip resources. The shared memory and register file capacity are limiting factors for TLP degrees. That is, if there are not enough resources to run all CTAs, the rest will wait for the running CTAs to complete their execution. A warp scheduler issues the warps in a CTA for execution, one by one, based on its scheduling policy. If a warp is stalled due to the lack of required resources or data, the warp scheduler selects another warp from the ready warp pool to be issued for execution. Higher number of available warps in each SM can potentially improve resource utilization within each SM. Multitasking can improve resource utilization due to 4 main reasons. First, as shown in the figure, hardware resources in the modern NVIDIA GPU generations have increased by 11 times compared to the old ones. Second, GPU workloads have applications with different resource demands. Third, some GPU applications suffer from their low TLP degree. Fourth, stalls occur for a variety of reasons in GPU applications. We briefly discussed spatial multitasking and simultaneous multi-kernel mechanisms and their shortcomings as previous solutions in the following slides. Spatial multitasking assigns CTAs of a kernel to a subset of SMs, where each SM executes CTAs of one kernel. This approach can potentially improve the utilization of the resources that are shared across the SMs, but has nothing to do with the resources inside the SM. Simultaneous multi-kernel execution techniques allow each SM to run multiple kernels and share its resources among the assigned kernels. Although SMK techniques provide higher opportunities to improve GPU resource utilization than spatial multitasking, there are 2 main challenges with SMK that limit its applicability. First, SMK can cause unfair execution among co-running kernels, and second, SMK causes higher cache trashing due to lower inter-thread cache locality, imposing performance and energy overheads. The existence of heterogeneity in resource demands of real GPGPU workloads is widely known. To analyze this fact in GPGPU applications, we simulate the applications in various standard GPGPU benchmark suites. We measure the application demand for register file and shared memory across different GPU applications. This figure shows the results for each resource. We report the current occupation and the real demand. Real demand essentially shows that how much an application needs a particular resource if there is no limitation on that resource. we make two key observations. First, some applications highly demand for larger register files and or shared memory while some others leave these resources underutilized. Second, there are some applications that do not utilize the register file or shared memory when we take their limited capacities into account. However, without considering their limited capacities, these applications essentially demand for more resources. Moreover, the question of how performance depends on the degree of multithreading was studied widely in the prior modeling work. One of the simple models captures an imaginary machine composed of many PEs and a large shared cache. As shown in this figure, as long as the cache is large enough to serve a growing number of threads, increasing the number of threads improves performance. At some points, the cache becomes too small for covering the growing access requests and performance takes a dip into the valley. However, as the number of threads increases more and more, the performance improvement starts again, where TLP is high enough to hide the memory latency. Hence, there are two solutions to stay away from the performance valley. One, limiting the number of threads to avoid reaching the performance valley, or two, setting the number of threads more than the performance valley. For applications that cannot increase the number of threads and have entered the valley, we can reduce the number of threads to avoid reaching the valley and provide the extra resources to the applications with high number of threads and hence increase resource utilization. In NURA, each SM executes CTAs belong to only one application, similar to the spatial multitasking, and shares its unused resources with the SMs running other applications demanding more resources. In the following slides, we show how unused portions of register file and shared memory can be utilized by other SMs as a remote register file and a remote shared memory to improve resource utilization and performance. NURA connects the SMs with a lightweight communication infrastructure and controls the data transmission at software level using a helper kernel. In the following slides, we explain the hardware support and the software support in NURA. To share underutilized resources in NURA, SMs are connected via bidirectional ring topology. The inter-SM network should manage remote accesses to on-chip SM resources. To handle the communication process, we put a low-cost hardware unit in each SM called inter-SM communicator. This figure shows inter-SM communicator unit in each SM. As the figure depicts, inter-SM communicator includes three main components: controller, buffer, and router. The controller abstracts the extra resources away and sends commands to the appropriate SM. When a consumer SM requires more resource than its available resource budgets, the controller finds the SMs that can provide their unused resources as remote resource for the consumer SM. The controller specifies the provider SM by checking the requested resource ID and warp ID. When the provider SM receives the request, it reads the requested resource ID, the warp ID, and the consumer SM ID. Then the provider SM sends the value back to the consumer. We use a buffer in the inter-SM communicator to temporarily store read values from the provider SM. For enabling hyperkernel read or write operations, NURA allocates a specific address space to this buffer. The network router has the same role of the conventional network on-chip routers and handles the packet transmission, avoiding deadlock, live lock, and starvation. We modify the CTA scheduler to decide how many CTAs can be assigned to each SM. The CTA scheduler knows how much register file and shared memory spaces are not used in the SMs. As a result, the scheduler assigns a number of CTAs to the consumer SMs by considering the remote resources on other SMs, and launches the helper kernel in provider SMs. The CTA scheduler also specifies which consumer SM can be serviced by which provider SM and vice versa. We also modify the warp scheduler as each SM can run two kernels, primary kernel and helper kernel. The way that the warp scheduler arbitrates between these two kernels is important. To ensure the primary kernel execution is not affected by the helper kernel, NURA always prioritizes the primary kernel, and hence helper kernel warps can be scheduled when all warps of the primary kernel are stalled. We modify the conventional GPU register file to tolerate the access latency of remote register files and provide the additional bandwidth to service non-local register access in the provider SM. This figure shows the proposed register file architecture. We use the unused register file space as a register cache, which can be accessed in the latency and bandwidth of a conventional GPU register file. We also implement the register prefetching to hide the latency for bringing register values from the remote register file to the register cache. In GPUs, instructions cannot dynamically access any resources. For example, if a specific register is needed during the execution and this register is not allocated statically at compile time, it's not possible to access it with native GPU instructions, but tandem condition instructions. Adding tandem condition instructions increases the lines of the code, which leads to performance degradation. To maximize the utilization of the resources by the helper kernel, we add new instructions to the GPU ISA. These instructions provide access to resources dynamically. We utilize free resources using the helper kernel. The helper kernel makes our design simple and is flexible enough to support different kinds of resources. As an example here, the helper kernel can allocate more register file space to other SMs through utilizing free register file and shared memory spaces of an SM. Second, helper kernel is scheduled alongside of the primary kernel on each SM that has free resources. Note that helper kernel can execute when there is no active warps belonging to the primary kernel. We evaluate NURA using GPGPU Steam version 4 and GPU Watch, modeling Volta-like GPU configuration. Use a wide range of workloads including Spatial, Linear, Parabol, and NVIDIA SDK benchmark suites to evaluate our mechanism. To show the effectiveness of our proposal, we compare the following designs. 1. Baseline, the state-of-the-art spatial multitasking implementations of GPU applications. 2. Ideal, ideally adding the maximum required remote register file or shared memory to the size of the baseline register file or shared memory, but with the same access latency and bandwidth of the baseline. 3. NURA Ideal HK, just running a helper kernel. 4. NURA running the helper kernel along with a primary kernel. 5. NURA Cache, the register file shared memory of NURA equipped with a caching mechanism applied only for remote accesses. And 6. SMK, the state-of-the-art simultaneous multi-kernel implementations of GPU applications. We compare designs in terms of overall IPC, STP, fairness, and energy consumption. This figure shows the relative performance improvement gained by NURA, NURA Cache, NURA Ideal HK, and Ideal normalized to baseline. We observe that NURA, NURA Cache, NURA Ideal HK, and Ideal improve the average performance by 13%, 21%, 27%, and 31% compared to baseline respectively. And the performance improvement of NURA is between 4% of Ideal, which clearly shows that the latency of accessing remote register file or shared memory is effectively tolerated using NURA mechanism. This figure quantifies quality of service of NURA and SMK across all workloads for a quality of service target per application and compares against a baseline. We define normalized progress as the normalized ratio of the NURA IPC to the baseline IPC. We observe that the normalized progress per application in NURA is greater or equal to the baseline. Hence, NURA meets the quality of service target for all workloads as the baseline does. This figure shows the relative STP of NURA and SMK normalized to baseline. We observe that NURA and SMK improves the average STP by 34% and 26% compared to baseline respectively. SMK does fine-grained sharing and hence outperforms NURA by 8%. This figure shows the relative fairness of NURA, SMK, and spatial multitasking. We make two key observations. First, NURA improves the average fairness by 42% compared to SMK mechanism. Second, spatial multitasking outperforms NURA by 19% on average. This figure shows the relative energy efficiency of NURA and NURA cache normalized to baseline. We make a key observation. NURA degrades the GPU energy efficiency by 5%, while NURA cache improves the GPU energy efficiency by 17% on average compared to baseline. NURA hurts GPU energy efficiency due to this fact that the energy per access of remote register is higher than a local register, while the energy per access to a cached register file or shared memory, which is remote, is the same as the local register file or shared memory. Multi-application execution in GPUs, a promising way to utilize GPU resources, is still challenging. Some pieces of prior work, for example SMT, have limited opportunity to improve resource utilization, while other works, for example SMK, provide fine-grained resource sharing at the price of unfair execution. Hence, we need to have a middle-way solution to reduce the negative effects of both. In this research, we introduced NURA to improve resource utilization and ensure fairness and quality of service, with 26% STP improvement for about 1% area overhead. Thanks for your attention, and I hope you enjoyed NURA's presentation.